Hi, welcome to es201 Computer Techniques. This is week 15 and this is a lab description, and this week we're going to be working with machine learning. So let me talk about, first of all, what is machine learning. And it's sort of a subset of other things. So let me first go through some definitions. Artificial intelligence is a branch of computer science, and it deals with the simulation of any type of intelligent behavior in computers. So it's a very, very wide ranging field. Now, within artificial intelligence is something known as machine learning, and that's an application of AI, and it provides systems the ability to automatically learn and improve from experience without being explicitly programmed. So machine learning is just a subset of artificial intelligence. And finally, there's something known as binary classification, and this is what you're going to be working with this week's lab. And binary classification is a task of classifying elements just given a set of attributes into two groups. And so you're going to use some sort of classification rule. So binary classification is a subset of machine learning, which is all a subset of artificial intelligence. Let me talk about how machine learning is different than what you've been doing so far through this entire semester, in fact. What we've been doing is often just writing code, and often we'll write functions. And you might write a function called myFunction, and it takes some parameter x and returns some parameter y. And before you run this, you actually write the entire code so that you can go ahead and specify what y is given x. Right? And so there's going to be some sort of input that goes in, and there wouldn't be an output that comes out. And this is very deterministic, right? So maybe you put 5 in, and then it's going to give 175.34 out, and it does every single time that you do it. You write this ahead of time, and then no matter what you go ahead and put in, you're going to go ahead and get some value that comes out. Machine learning is actually kind of flipping this whole thing on its head. So here what you do is, instead of writing your function ahead of time, you actually have an empty function and you don't know what's in it. And what you do is you just shovel a whole bunch of input into it. So you go ahead and put a 5 in, and a 4 in, and a 3 in, and a 19, and you just put in all sorts of stuff. And then what you do is you just kind of sit back and see what comes out. So, you know, if you put a 5 in, and you get 174 out, you put an 8 in, you get a 16 out. And you go ahead, and if you do this enough times, you can put an algorithm in such that it learns to sort of predict what it should output given what a particular input is. And after you've done that long enough, you're going to end up essentially having some code that's kind of written itself, but it's actually not code. It's going to be a series of numbers, and we'll see that in a bit. But it's going to go ahead and write itself. And so then at this point, after you're done with it, then you can go ahead and give it a number, maybe the number 5, and then it can go ahead and give you an output. But what you've done is you've used a bunch of examples to generate the code that actually goes in here. So what's different? Well, you don't have to write the code, but you have to have a whole bunch of examples where you know the output at the end, what's coming out of the other side for it. And so that's why you've got training examples, and then you've got testing examples. So we'll talk about this more in detail here. So as I mentioned, we're going to do binary classification. And you've actually probably run into this a lot already on the internet. The reCAPTCHA is an example of this, right? So here I show a typical thing where it says, you know, select all the images with bridges. And the computer's actually kind of gone through and done its own identification of what it is, and you're just kind of testing yourself versus that. That's binary classification. Each one of these images, either a bridge or not a bridge. Either a bridge, not a bridge. Yes, no, yes, no. So that's binary classification. Let me talk about how prediction is a little bit different than regression, right? So we're doing prediction. So normally, let me talk about regression. You've run into this before. So for example, if you had a bunch of data values, x like this, and then for each one of these x's, there's a given y. And if you wanted to be able to sort of predict what the y is going to be given an x, right? You might do a linear regression. Put a line through here, and then no matter what value of x you have, you can go ahead and determine what the corresponding value of y should be. Right? So you can have some sort of linear equation for it. That's a linear regression. But you can do other types of regression. You can do something that's called logistic regression, and so that's what's applicable for binary classification. Because here you've only got two outputs. Right? You've got either it's not an image or it is an image, a 0 or a 1. So the outputs over here, the y values, are either 0s or 1 and nothing in between. And then you've got some sort of attribute that you're looking at, something. And if you were to go ahead and look at a bunch of examples, you might have a whole bunch where it says no, 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 no. And then as this attribute becomes a certain amount, then you start to say yes, 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 yes. And so you've got this kind of dividing line that now your line looks like this. And so if you want to go ahead and sort of fit this to a curve, a common one to do is a curve that looks something like this. It's going to be continuous, right? And so anytime you've got your attribute that's up above this line, you're going to say yes, and down below this, you're going to go ahead and say it's no. This is called a sigmoid function. And so here's actually the equation of that function. If this attribute was a variable z, and you wanted to go ahead and determine what that purple line was, which was sigma, you go ahead and put that value of z in there, and you can get that value. So let me just kind of show. So if z was exactly 0, so if this right here was 0, the sigmoid function is going to give you 1/2 at that point. So it kind of says that it's like 50-50, doesn't know if it's yes or doesn't know if it's true. But if you go down to the negative sides of z, you end up very small values. It's fairly sure it's not. If you go up to larger values of z, like 3, then it's got like kind of a 95% confidence for it. What you're going to do in the lab this week is you're going to be working with character recognition, and this is a classic testing data set for all machine learning. There's a data set called the MNIST data set. As I said, it's a standard for machine learning. And what it is many, many examples of people that have handwritten the digits 1 through 9. And so what you're going to be doing is classification. You're actually going to be determining if a particular digit that you see is, for example, is it a 3? So you're going to go ahead and write a code that can go ahead and look at one of these images and go, yes, that's a 3. It might look at another one, say that's not a 3. Yes, that one's a 3, or that one's not a 3. That's kind of the idea. This is a very, very large data set. It's actually got 60,000 training images and 10,000 testing images. Remember, 60,000, this is the ones that you shovel in to go ahead and create your function. And then once you're done, the standard is to go ahead and use these last 10,000 to go ahead and see how well you did. Each one of these has already been what's called classified, which says that this image right over here is a 1, this image right over here is a 0. And you need to have that pre-classification in order to test these algorithms. You're going to be doing what's called a neural network. You've probably heard this term before. Let me just kind of mention the idea. In general, a neural network takes a bunch of inputs, and then what it does is it goes through a series of layers. So it takes all your inputs, and then it does something with that particular attribute, sends it into another one, does something with it, goes through, and at some point you're going to get some type of output. This whole thing right over here is that machine learning curve that we just mentioned that sort of generates itself. And in binary classification, all of your inputs are, well, it's this image right over here. So this is what goes in. And then this sort of black box-ish neural network works on. And then what comes out is a single value that's either a 0 or a 1 that says, yes, that's a 3, or no, that is not a 3. You're going to be doing a particular application of a neural network called a one-layer logistic regression. Let me explain what that is, right? So now here's your diagram of your neural network, but you've got one layer, just this layer right over here. You take all of your inputs, so these would be like the values of x. This is actually your image right over here. These are actually pixel values. And then you've got this weight, which is what means how important is that pixel value. And then what you're going to do is after you've weighted each one of these pixel values, you'll add them all together and you'll get a value z. All right? And so once you have that value z that comes out of it, you're going to come over to your logistic function. This is where the logistic part comes in, the sigmoid function. You're going to look at your value of z and then find out what that is and the corresponding value. Remember the function here. It's also known as the activation. This is that sigmoid function. You plug in here, and if anything above 1.5, you'll say, yes, that's true. Anything below 0.5, you say, no, it's not true. All right. So here's the function for this the entire logistic regression. That value of z, you take all your pixel values, and you multiply them by some particular weight. You add them all together. There's one over here called b, which is the bias. You don't input anything to that. You just go ahead and add it. So think of like ax plus b, right? You always just got to add this constant to it. So there's actually this final value. So you've got a whole series of weights, and then this value b that goes into that equation there. Now, what you need to do when you write these is you first train your model, and then you can test it. So training your model, essentially, the question is, what are the w's? What are those weight values? All right, so you've got your image, and what you're going to do to train it is you're going to take an image. It's going to be this pixelated image of it, and you're going to go ahead and just convert that into a one-dimensional array. You'll see why that's a little bit easier. So you're going to go ahead and read down all those pixel values and pixel values. You're going to reshape this two-dimensional array into this whole series of pixels, and that's what's known as the variable x. All right. And each one of those pixels has a particular value. And so I kind of show some examples here. And so this top one right over here, if it's completely black, might be 0. Completely white, it's 1. Right? We've worked with grayscale, so these are all just sort of scaled to 0 and 1. So completely white is 1, completely black is 0. A gray one over here might be 0.8, something like that. And so you now got this array of values x, and the size of that is going to be the number of pixels in the image. Then what you do is you take each one of those pixel values and you multiply it by the weight w, and then you add them all together according to that equation that I showed you before. And when you're all done, you've got a value z, right? And so then what you're going to do is you're going to put that into that sigmoid function and see what it predicts. And it's going to come out with something output, and maybe the sigmoid function says, oh, it's 0.313. Well, when you're training your model, you know whether that should be true or false. And so then you're going to say, well, my model said it was 0.313, but maybe it was actually the number 3. And so that means that it's not giving you the correct answer. You want something greater than 0.5. So you now need to adjust those W's. You need to go ahead and do some tuning to what those weight values are. Right? And when you're tuning those, think of a lot like when you're steering a car, you're going to go ahead and adjust them proportional to how wrong you are, right? If you're just a little off the road, you just sort of turn the wheel. But if you're really far off the road, you got to yank the wheel. So that's kind of the idea. And what you're going to do is there's some math that's involved with it, and I'll go ahead and you don't need to do the math. I'll tell you the way that you're going to do this is you're going to adjust the values of W, delta W, by this equation here where you've got A minus Y. So this is sort of how wrong you are, right? A is what your model predicted, that 0.313 above. Y is actually what it was. It's either going to be a 0 or a 1, depending on that particular image, whether it was the one you wanted or not. You're going to multiply it by that particular pixel value, because each x has a corresponding weight value. And there's this last parameter, alpha. It's called the learning rate. It's how quickly you're going to adjust the whole thing as a whole, not each individual pixel. I give you this value. It's something over there. We're going to actually use the value 0.1. All right, so I'm going to go through even a more concrete example if you're still maybe not entirely clear how this works. So imagine I had these 3 training images right over here, and what I want to do is I want to determine whether that is actually an X, right? Okay, so you can imagine that this one right over here, that kind of looks like that's an X. That one kind of looks like that one's an X. This one doesn't look like an X, right? So there's going to be some labels for all of these, right? And so these first 2 would be labeled 1, meaning yes, they are the image. The last one would be 0. Okay, then what you do is you then go ahead and take each one of these pixels and go ahead and convert that into a one-dimensional matrix. So these 9 pixels go into that column, these 9 pixels go into that one, and these 9 pixels go into that one. And you do that for as many training images as you have. And the reason we do that is because with MATLAB we can actually operate on that entire matrix with one step. Right? So then what you need to do is you need to determine all those weight values. Remember all the W's, right? So each one of these pixel values you're going to multiply by that value W. Initially, you don't know what those W's are, so I guess we'll just start off and say, well, maybe they're all 0, right? And then what you're going to do is you're going to be tuning your model. All right, so what you do is you plug in all those pixel values, you multiply them by the W's to go ahead and get your value of Z and send that into the sigmoid function. Well, initially, right, all the W's are 0, so if you look, if all those W's are 0 in addition to the B, Z is going to be 0, so that means you're just going to have that point there, which means initially, you're going to end up with an activation of 0.5, which means, I don't know, half yes, half no. So now what you need to do is to go ahead and adjust those values, okay? So we're going to adjust the delta W's by, we're going to take each activation value versus minus y. So for example, if I look at that first image, the A value, the activation is 0.5, and y is 1. So that's going to be 0.5 minus 1. It's going to be minus 0.5. I'm going to multiply it by the pixel value and then the learning rate. As I said, that's a constant in this problem. It's 0.1. Right? And so you put in all those pixels. You're going to end up with all these different values of delta W you need to change. And so for each one of those weights, you might have a particular value that looks like this. Right? And so this is that first go round. And then what I'm going to do is I'm now going to go ahead and adjust those weight values by that delta W. So here are my new W's. Notice they're all now different. Like that top one, I went ahead and adjusted it at 0.0833. The next one, 0.2823. I multiplied those all by the learning rate, which was 0.1. That's why there's those extra zeros in there. And now I'm going to go ahead and do the whole thing again. I'm going to go ahead and rerun it. I'm going to take all my pixel values and multiply them by those weights. However, this time, not all the weights are going to be 0, so I'm not going to end up with a value of z that is 0. Every time you do this is known as an epoch, and so this would be 1 epoch. And the number of times you do this is the number of epochs for your learning function. Right? So maybe you do this a second time. And now, since your weights aren't 0, you end up with some new values of activation. Now I've got a 0.5295, 0.5285, 0.4975. Notice this one is starting to go toward the 1 value through the true value, and the not true value. So it's slowly learning. So what you're going to do, you want to kind of do this for a little bit. So you're going to go ahead and find some new delta W's. So again, now I'm putting my activations now are like 0.5295 minus 1, or 0.4975 minus 1. And then go ahead and calculate my new delta W's. Right, that's epoch 2. And go ahead and plug those back in. So now I got some new weight values. I've now adjusted this some more, a little bit more. And go ahead and once again, multiply all your pixel values by those weight values. Calculate a z value, look at your sigmoid function, and figure out what it is. And now you might have, sorry, it's overwritten, but these are 0.5568, 0.5548. See, they're getting closer to 1, 0.4942. It's getting smaller. And so it's slowly learning. It's getting better and better at predicting each one of these values. So you keep doing this, and you're going to go and do this for a particular number of epochs, and again, it's specified in the problem, the number of epochs that you do. So you need to learn for a while, and at some point, the error rate gets pretty low. All right? So once you're all done with that, and you've trained your model, now you can go ahead and test it with some image it hasn't seen before. So now what you'd like to do is say you've got this image here, and this is my test image, right? And this one over here, hopefully that looks like an X. Hopefully it's going to go ahead and tell me that that is an X. But we'll go ahead and test it. So we're going to go ahead and take my test image, break it down into a one-dimensional array. So right, pixel 1, 2, 3 is 1, 2, 3. Pixel 4, 5, 6, 4, 5, 6, etc. And then I go ahead and multiply it by the final weights that I had. That's going to go ahead and give me a z value. All right, and so maybe it gives me the z value of 1.1955. Plug that into my sigmoid function. So if z is 1.1955, I look over here. That looks like it's right about at this point right over here. So what does that tell me the activation is? It's about 0.69. Remember, anything above 0.5 is yes. And so it says, yes, this is an X. So it looks like my function, my machine learning function, did okay to go ahead and predict that that image right over there was an X. All right? So in your program, what you're going to be doing is you're actually just going to be putting in characters and determining whether they are the actual character that you wanted. Now, you can do non-image machine learning. Machine learning isn't just identifying images. You can do all sorts of stuff with machine learning. So in this example, right, we took an image and we went ahead and looked at particular pixel values, and each one of those pixel values had a number associated with it. But there's other things you can do with machine learning. Some common applications of machine learning is that's used to go ahead and determine what the chances that someone's going to default on a loan. They're actually used very commonly now in social media moderation to determine whether a particular posting should be flagged. It looks at credit card fraud to determine whether a particular charge is fraudulent or not. It also does particular recommendations. Should you recommend that product or not? So you can see these are a lot of binary classifications, right? The user is going to default on the loan or not. It is a valid posting or not. It is fraud or not. It should be recommended or not. Those are all binary classification applications, and you can do all sorts of stuff. And actually, after you go through the lab this week, you're going to go ahead and modify the program you wrote, and what you're going to do is you're going to identify whether something is a pulsar. All right. Now, when we talk about what pulsars, the way that we go ahead and determine whether something's a pulsar is you've got radar on the ground, and it's kind of looking up at the sky, and it's constantly sort of listening, and these electromagnetic waves are coming in. And what we want is our machine learning to say, hey, I'm looking at a pulsar. And how does it do this? Well, what you're going to do is you look at this particular signal that's coming in, and you compute some statistics. And there's what you can do. You can go ahead and find out the mean of that signal that's coming in, the standard deviation, the kurtosis, the skewness. There's all sorts of stuff you can do. And there's actually 8 common attributes that are done when we're doing to identify a pulsar. Each one of those 8 attributes has a number associated with it, right? So here is what the mean value of the signal is, right? There's the standard deviation of the signal. Each 8 of those, you can imagine, those are just like 8 pixel values, and you go ahead and stick those 8 numbers into your machine learning algorithm. And then when you train it for each one of those signals, it's either going to be a 0 and a 1 classification that says, yes, that's a pulsar, no, that's not a pulsar. And when you're all done, you'll have something that can go ahead and look at a particular signal coming in with those 8 attributes and say, yes, that's a pulsar, or no, that's not a pulsar. So that's how you're going to go ahead and finish out your lab, is going to be modifying your previous program to do that.
Now, this week's lab is going to be the most challenging that you've done all semester, and I recognize that. And so we're going to do lab just a little bit differently to kind of help you along. So first of all, let me go ahead and show you. In week 15, this is our last week, when you come in and look at your week 15 lab, there's actually a file here called logreg.mlx, and this is called a MATLAB script. So go ahead and take that file and go ahead and run it. You can run that either in the online compiler or on a standalone environment. And if you do that, what you're going to do when it opens up is you're going to see a file that looks sort of like this. And these are going to be your instructions. And what the MATLAB script does is you can kind of slowly work through and develop your program step by step. So it's very similar to what we've done before, but even more broken down. The way MATLAB script works, right, if you see here, there's this upper section, and sections are marked by these blue lines. In each one of these sections, there's going to be some instructions. And overall, anytime you see your code here, you're going to add some code. So this first section over here, there's actually nowhere you need to do it. All you need to do is go ahead and just run this particular section. And you can run a section. If you go over onto the right-hand side, and where these little blue numbers are, you can go ahead and click that blue bar. And what it does is it runs that code. And so what we see over here on the right-hand side, it gives you some output. And what we just see is that we've loaded some training images and loaded some testing images. So then go ahead and just go down to your next section here. Again, there's some instructions. It shows you some code. And this second section here, again, there's nothing that you need to do. You can just go ahead and run that section of code after you've read it. You go ahead and run it. And what it's going to do on the right-hand side is go ahead and give you the output. And here it's going to go ahead and show you a random image, right? It says that this is the number 8. If you want to rerun that section of code, you can just click that blue bar again. Again, it's just showing you random images that it's loaded, and it tells you what that is. So now we come down to our third section, where you need to reshape the data set. And now you see your code here. You actually need to add some code. So you can just click in here and type, and then you'll need to go ahead and type your code in here. And then when you're happy with what you have, you go ahead and click that blue bar to run it, and it will either tell you whether it worked or not. These assert functions, all this, don't change any of that. That is just going to go ahead and test of whether what you've done is working properly. And then you're going to go ahead and just continue to step through the entire thing. And when you're done, you'll have finished out your machine learning algorithm. So I kind of give you a lot of template to go ahead and read through and do it. Okay. Now there's 2 steps to this week's lab. When you're done with that, now you're going to go ahead and work on that pulsar assignment. And so that again is going to be done in MATLAB Grader. So you're going to come over to MATLAB Grader into week 15 and go ahead and open up that week. And you're going to see this problem called pulsar identification. And this is going to be kind of like a similar type of program where it's going to tell you what to do, and you can go ahead and read the files. Here, what you're going to do is you're going to modify the program that you had in MATLAB. And if you go over and back into MATLAB, just save this as a MATLAB function, as a .m file, and the instructions tell you how to do that. Then you go ahead and just make some small modifications to what you did from your image modification to do pulsar modification. Submit that for testing as well. So there's kind of 2 steps. The script helps you write your initial program, and then you need to modify it for the end. So, well, if you have any questions, let me know, or go ahead and I would say attend lab and see the TA and get some help from him. All right. Well, good luck this week.